everyone, we are the senior design team in charge of the four-wheel drive electric FSAE race car, and today in this presentation we're going to talk to you a little bit about our design and analysis process of the race car. So to achieve this, we designed an upright which will mount our motor and also house our gearbox, which would reduce the output of that motor. This motor will also be water cooled using a water cooling jacket designed by us, and our hub, which will transfer the power, will have provisions for mounting our brake set.
Tasked with designing a race car that features 4 in-wheel motors with a 10-inch diameter wheel. The package must allow for 35 degrees and 25 degrees of steering motion, as well as 1.5-inch travel in the up and down directions. Our design adapts components of the previous combustion cars, designing an upright and a hub to hold the gearbox. We also designed a backplate for mounting. This component was crucial for attaching the gearbox as well as the motor together. After creating a CAD model and testing its movements, we discovered interferences that hindered the package's full motion. To address this, modifications were made to the suspension. The steering arm as well as the A-arms locations were changed, and as well as increasing the scrub radius. With these changes, the package moves with no interferences.
In Racecar, our car will have 4 electric motors inside each wheel. So first, we will give an AMK motor which has big dimension and maximum power is high with 21,000 RPM. For the purpose of the battery gear design, the suitable dimension for an in-wheel motor, research on different motors were conducted using the liquid cooling system and high level. After many research, the NK420 was selected. It had good dimension, good rated power, and the maximum speed is 12,000 RPM. It has a significant effect on the project and it allows us to use a single stage gearbox.
For the client, we determined the power demands that would be placed on the electric motor for its most grueling track, as outlined by FSAE. We found the average engine power for the vehicle on this track through the use of simulation software. From this average, we could begin to estimate the maximum average heat output we could expect from our vehicle setup. The value for the average heat loss was then inputted into ANSYS Fluent, along with other constraints to determine the optimum dimension and topology for our cooling jacket. Through an iterative process, we were able to come up with our final design, a double helix topology.
In order to acquire the desired torque without the use of large and heavy motor, a gearbox is required. Finding the speed required revealed that we will need a 7-to-1 reduction ratio. This will reduce the speed from 12,000 RPM to about 1,700 RPM and increase the torque from 12.6 Newton meters up to 88.2 Newton meters. The dimensions of the gearbox are crucial to meet the size constraints of our package, so a planetary gear system was chosen as it provides the necessary reduction in a slim package. We were advised to look into off-the-shelf gearboxes and found that Apex Dynamics offers a wide variety of options for planetary gearboxes. The AB060 gearbox was selected as it met all our requirements while still meeting all our constraints. Thank you for watching and have a good day.